Hello everyone, this is Krishna from Sony, and in this video I'm going to talk about some of the papers and demonstrations from Siggraph Asia 2021. So Siggraph Asia 2021, Siggraph Asia in general is a conference and exhibition on computer graphics and interactive techniques in Asia. It was held in December 2021 and the conference took place in a hybrid format, virtual and online. I had the opportunity to go to Tokyo International Forum to attend the conference in person and witnessed some of the exhibitions, demonstrations and talks. It was a really good experience and I'm going to talk about this in this video. So I could see that there were a lot of impressive demos based on VR, XR based simulations. Parallel, so this is one of them, Parallel Ping Pong by Sony Computer Science Laboratories. So parallel ping pong is a parallel interaction with multiple bodies. Here the two robot arms, which was controlled by a single user. And to reduce the user workload when controlling multiple bodies, they added an automatic view transition between different bodies. And they also added an autonomous body motion integrating the user motion, as we saw earlier in the video. There was also a really impressive award-winning interactive VR movie Clap and XR movie Beat by Cinema Leap and Wow Wow. So it was an interactive movie where the user could interact with the characters and could be really immersed in the scene. Then there was also this real-time image-based virtual try-on by University of Tokyo. They proposed a robust real-time image-based virtual try-on system, and they formulated this problem as a supervised image-to-image translation problem, and you're using a measurement garment and for a better understanding. And then they captured training data with custom actuated mannequin, and the user only needs to wear a measurement garment to try on many other different target garments. So another impressive demo was this Frisson Waves by Keio University Graduate School of Media Design. So frisson is a mental experience of body reactions such as shivers, tingling skin and goosebumps. So when listening to a certain type of music, orchestra, or maybe if you're seeing the ending of a Christopher Nolan movie, people experience this sensation of shivering or tingling or goosebumps. But this sensation is not shareable with others and is rarely used to enhance experience in a live performance. So they proposed this Frisson wave sharing system where which was a real-time system to detect, trigger and share frisson in a wave-like pattern during music performance, so that it could enhance the experience of experiencing these musical performances. There was also this Aromatic Garden by Tokyo Institute of Technology and the University of Arts London, so which proposed a multi-sensory olfactory game which was called the Aromatic Garden, and it offered a user experience through the combination of new olfactory technology and art. So players of this game must use the sense of smell to navigate and collect scents, and that presented an engaging and challenging experience. So here this player has to go around based on there was a hardware provided for smelling different elements, and based on that they had to navigate in this environment. Moving on to some technical papers. So some of the popular paper topics were character simulation, turbulence and fluids, face images and animation, metaverse and neural rendering, amongst others, which are some, these topics are expected as it's a computer graphics and interactive techniques technology conference. And based on my topics of my interest, I'll present papers on face images, neural rendering, character simulation and some other papers in this video. So I'll first present papers on face or body generation methods. So this first paper was called Barbershop, a GAN-based image compositing using segmentation masks. So here the authors, they propose a method to transfer hairstyle from one image to another For example, if you have this image in the top left and the desired hairstyle is from the image from this image in the top right, and yeah, their method enables generation of the image in the bottom which has his face and her hairstyle. So what they are essentially doing is that they propose a novel latent space projection method for StyleGAN2. So what they do is they take a pre-trained StyleGAN2 model on human faces, and for a given input image they optimize for these FS code. So the F here is the structure tensor and S is the style code. So what exactly are these? So just to recap, StyleGAN2 has a hierarchical architecture in which we start with a 4x4 constant input and upscale it to get 8x8 output, which is then upscaled to get 16x16 output, which is then upscaled to get 32x32, and this process is continued to get the final image of 1024x1024 resolution. So the structure tensor here is the intermediate output of the StyleGAN2 generator here of size 32x32, and yeah, the S, the style code. So in the generator architecture, a random noise which is called Z is passed through an 8-layer MLP, and which gives us these W vectors which are these 512 in dimension and 18 in number. So these 18 vectors are injected at different points in the convolution block, and out of these 18 vectors they use these last 11 as the style code in this work. So they could have optimized for any other intermediate output of StyleGAN2, but in their experiments they probably found that optimizing for these specific style or these specific intermediate outputs like these 11 W codes and this intermediate 32x32 output gave them a good trade-off between controllability and image reconstruction quality. So this is their overall pipeline. So suppose they want to generate an image which has this top girl's face and the bottom girl's hair, and the hair color might be from the either of the two. So how they do it is they first take the two images and reconstruct the image using their FS code latent space projection. So using some of the shelf techniques, they get the segmentation mask of this face which has most of the features from this girl and hair from this girl, and as their aim is to combine top girl's face and bottom girl's hair, they generate, yeah, as I said, a facial segmentation masks in that manner. So figure D is what happens if they try to do this hairstyle transfer in W plus space, which is a W align face, and yeah, so you can see that while hair style is transferred to an extent but other features are not preserved, which is something undesirable. So how we work here is that using the target mask in C, they blend the structure tensors of the two images, and the style code is further optimized by also using this segmentation mask and style loss. So the style loss taken from the neural style transfer architecture. So and then they can use the style from top image if they want to generate the blonde hair color, and they can optimize for style loss with the bottom image if they want to generate the this bottom which is like brown hair color from this bottom girl. So which is how they get the image H and image I. So these are some of the other results of this work. So as you can see again, so this girl's face and this girl's hair, and yeah, based on that they are able to change hairstyle of any given input face. So now as this hairstyle transfer actually is making use of this segmentation map, which is how they are able to selectively transfer hairstyle from one face to another, they can use the same segmentation map to transfer eyes, nose, and skin color from one image to another, as you can see in the top, middle and bottom row respectively. So in the top row you can see the eyes are changed based on a given reference input image, and in the middle row the nose is changed, and in the bottom row skin color is changed. So they're able to transfer other features as well, because and it's essentially the same method as transferring hairstyle, because everything is making use of that segmentation map. So some of the limitations of this work is that it can struggle in some corner cases, such as when the pose of two faces are very different, or if the hair is like covering a part of the face, as you can see in this input image. So it can struggle in those scenarios. So moving on to the next paper. So this next paper, it's called Dynamic Neural Face Morphing for Visual Effects. So dynamic neural face morphing for visual effects, this is a work by a company called Digital Domain, and it was used in some commercial campaign in which they generated an aged image of David Beckham using this method. As you can see in this example, they were given this input image of David Beckham and they generated this image, which was an aged version of his face, I mean the side view of his face. So how this method works is as follows. So their method is relatively straightforward. They use an encoder-decoder architecture to reconstruct an image where the encoder is shared, it's the same for all images, but the decoder is identity specific. Then they linearly interpolate between different intermediate outputs of decoder to alter the shape, texture and skin tone of the generated face, as shown in this figure. Like by altering this intermediate output, they are able to change the face of the generated shape. With this intermediate output, they are able to change the texture, and with this they are able to change the skin tone. So they already showed a UI in which they could use these three shapes as a basis to change the shape, texture and skin tone of any given input face. And yeah, as you can see in this image, so if they selected this skin tone, this texture and this face, they got something like this. And then they used some image stitching techniques to they extracted this portion of the face, applied this interpolation and got this result, which was stitched back in the original face. And and they could likewise do other kind of interpolation as well. So limitation of this work can be that it needs similar type of faces to work, and maybe the separation of attributes can also be better, but I mean they are using a very simplistic architecture, so so there is obviously a scope of improvement there as well. So moving on to the next paper. So this paper, it was called Semi-Supervised Video-Driven Facial Animation Transfer for Production. So this paper proposes a method of transferring facial motion from a given 2D video of a talking face to a 3D character. So as a data pre-processing step, they crop the facial region from the input videos so that the network can mainly focus on transferring facial expressions. Then they propose a two-step method for their task. First, they learn an image-to-image model for transferring expression in an unsupervised manner. So here the method is unsupervised in the sense that the network is not trained for transferring expression from person to 2D rendering of this character. So this first part, although they are using a different model, it's quite similar to first order motion model, IC Face and other similar works, and the network is trained for the task of self transfer of facial motion and is later applied to the 2D image of this 3D character. So then, as they have access to the 3D model of the character, they generate a data set of different expression of the 3D model and it's rendering from a frontal camera view, and they save the rendering and blend shape coefficients and train the neural network to map this image to the blend shape weights. So during inference, how this works is that given the talking video of this person as the driving video and image of the character as a source image, they generate a 2D animated video of that character. Now, if this concept of animating a still 2D image is unknown to you, and if you would like to know more about it, you can check out our video on the collab demonstration of first order motion model. The demo is available in Japanese and English, and you can find the link to those videos in the video description. So moving on, after obtaining the generated animated video, it is used to get the blend shape weights via this second network, which is applied to the 3D model to get the animated video of this 3D character. So this is how they perform the aforementioned data pre-processing. Facial region is cropped and aligned from the actual footage, and they render the 3D character and store the 2D image and corresponding blend shape weights. So similar to the previously presented work on dynamic neural morphing, which was also by this work is by the same authors as the dynamic neural morphing paper that was presented just before this. And they again here they use a shared encoder and a decoder, it's identity specific. So yeah, and it's trained for this task of self transfer to next. Yeah, and that's how, I mean, the loss is for the task of self transfer. So this is how their architecture looks. So you can see the source video like this, and they are able to do this is how the image to image transfer, and then they transfer from image to image, they do this image to geometry. So impression and limitations. So some of the limitations of this work were as follows. Although the generation result for 3D character looks quite good, the model struggles with different lighting and background condition, which might be down to their use of, again, the relatively simplistic facial transfer in the rendered image domain. And also, as they crop the input 2D video around the face, this method is not really designed for pose transfer of between the driving video to the source image. Moving on to the next paper, which is called Live Speech Portraits, which is a real-time photorealistic talking head animation. So the aim of this work is to generate photorealistic talking head animation, which is driven by audio signals at over 30 frames per second. So how this works is that given an arbitrary audio stream, they want to generate an expressive and realistic video of a talking target person which is consistent with the audio stream. So this is how their method looks like. First, they generate facial dynamics, head poses and upper body motion from audio, and then using that they generate temporally consistent face images. How this works is taking this audio stream as input. The GRU based network outputs a representation which is then used as input to networks responsible for audio to mouth movement mapping and audio to head motion mapping, and the output of these two networks are then used to finally generate the output frame of a talking person conditioned on some candidate images of that person.
Good morning. In less than an hour, aircraft from here will join others from around the world, and you will be launching the largest aerial battle in the history of mankind. Mankind. That word should have new meaning for all of us today. consumed by our petty differences anymore. We will be united in our common interests. We are fighting for our right to live, to exist. And should we win the day, the 4th of July will no longer be known as an American holiday, but as the day when the world declared in one voice, we will not go quietly into the night. We will not vanish without a fight. We're going to live on. We're going to survive. Today we celebrate our Independence Day.
So some of the limitations of this method are as follows. This method, it does not always capture the plosive and nasal consonants properly. So yeah, most of the kind of consonants that require significant breathing out of air, you can say, and audio far outside the training span may also generate unsatisfactory results. And yeah, and emotions and expressions are not really captured as well, and there is no scheme for explicit control of gesture or lighting. So moving on to the next paper. So this next one is called Rendering with Style, Combining Traditional and Neural Approaches for High Quality Face Rendering. So this is a paper by Disney in which they combine traditional and neural approaches for high quality face rendering, as the title suggests. To give a brief background, traditional face capture methods, which typically use multi-view stereo camera and temporal tracking to reconstruct the 3D geometry, but these methods only construct the skin and these methods only construct the skin and they fail to capture other facial features. So the authors of this work, they propose a method that takes high quality ray traced facial skin masks such as this and generate a complete face with that, such as this. So their method builds on top of these traditional face capture pipelines. So essentially they propose a method to project the skin render to the latent space of StyleGAN2. Their method is novel as this method can take in a batch of input skin renders and produce faces of same identity. They do that by their latent space projection in the S space or style space. So this projection onto the S space is not their proposal. They took it from some other paper, but they apply some constraints on these optimized latent space codes, such as they should be close in the S space for the identity to be same, and some of the other constraints as well for this method to work with skin renders and not complete face images, which is novel and which is a contribution. So then they further see that the naive latent space projection result, it's good going from here to here, but this latent space projection, it fails to capture some of the finer skin features. As you can see that here the skin has some texture which is slightly rough, and here it's really smooth. So what they do is that after getting this result, they blend the original skin render on top of the generated face to get the final output, which now has all the finer features of the skin render and is higher in quality. So these are some of the results which show that their method works for different skin colors and face shapes. And yeah, here we can see that their method can generate different expressions with the same identity. And their method can also capture illumination changes. And yeah, some further illumination and lighting changes. Yeah, their method, it can also capture viewpoint changes as shown in this result. So in summary, so I mean, some of the discussion points about this paper, it's like they state dataset generation of face images as one of the possible applications of this work due to their ability to handle viewpoint, illumination, and expression changes. But as a limitation of this work, they mentioned that wearing all of the above at the same time can lead to poor results as well. So moving on to the next topic, I'll present a couple of papers on neural rendering. So this first paper is called Nerve Factor, Neural Factorization of Shape and Reflectance Under an Unknown Illumination, which has some of the same authors as the original Nerve paper. So the aim here is that given a set of photos of a scene and its camera poses, I mean, they are dealing with the same sort of data sets, same sort of scenes as the original Nerve paper. Their proposed method decomposes the scene appearance into a 3D field of surface normals, light visibility, albedo, and spatially varying BRDF. This allows novel view generation and relighting with a single point light source or an arbitrary light probe, as you can see here. So in order to explain their method, I'll just briefly recap the original NERF model. So how the original NERF model works is that the position XYZ is fed as input to a multilayer perceptron which outputs density at each point and an intermediate output. This intermediate output is combined with viewing directions and is fed as input to a second MLP which predicts the RGB color at that location. So the original NERF, it's capable of view synthesis but not capable of relighting and material editing. So how NERF factor works is that it uses the first part or the first MLP of NERF as is. In fact, it is pre-trained. It is exactly same as the original NERF, like not only the same architecture but also the same weights as a trained NERF is used for this first half here. Then they use the NERF predicted density to analytically calculate normal, accumulated transmittance, and expected ray termination point or the surface location. So the surface point, intermediate output, which is the intermediate output from first MLP, and viewing directions are used as input to these MLPs which predict light visibility, BRDF, albedo, and normal. And all these different factors are then used to render the final scene and compared to the ground truth version. Now, a question that needs to be asked here is that if you can get normal and transmittance from this NERF predicted density, we are analytically calculating the surface point and accumulated transmittance and normal from this density, then why do we need a normal MLP to predict the normal, and why do we need this light visibility MLP to predict that as well? So the answer to this is that in their experiments, the authors found that the analytically calculated normal and visibility maps are noisy, and hence a separate MLP is used to get a smooth estimate of these quantities, and this smooth estimate is integral to get good results as it leads to better optimization of NERF. And the BRDF MLP is trained on a separate dataset that had 100 types of materials for data driven prior is used there, and light is passed, it's passed in the mask format, which they say helps in better generalization here. So some of the intermediate results. So as you can see in this figure, the left, it's the analytically calculated surface normal and visibility map, and they are quite noisy and are granular. So using them directly leads to poor results. They found that in their experiments. So they use an MLP to get a smooth estimate of them. And then this smooth estimate is used by the other networks to finally get the final output. So these are some of the results. So this is the results. So this is the surface normal visualization, visibility, and this is the final rendering. So they pass this light source in the masked format as was shown in the architecture diagram, and they could get the final rendering. That. So some of the talking points of this paper were as follows. So pre-training of certain networks, like the first part of MLP, which was not trained from scratch. It was the first part of the model, the first MLP. It was not trained from scratch. It was taken. It was exactly same as the one that was used by original nerve model. So that kind of pre-training and smoothness constraints were crucial for good performance. And as for limitations, while this work provides for better controllability than nerve, it does not really improve on some of the other limitations on nerve, such as per scene optimization, slow inference, inability to handle moving objects, etc. So the next paper, it's called Neural Frame Interpolation for Rendered Content. So in this paper, the authors propose a frame interpolation method specifically designed for animated or rendered content by leveraging they leveraged certain auxiliary features such as depth, normal, and albedo to do this frame interpolation, and they are able to achieve state-of-the-art results for real animation movies. So this is how their architecture looks like. So in this work, they assume that they have full input for every nth frame in addition to they have full input for every n frames in addition to auxiliary feature buffers that they say it's cheap to evaluate, such as depth, normal, and albedo for every frame. And they propose solution for leveraging such auxiliary features to obtain better motion estimates and more accurate occlusion handling, and to correctly reconstruct non-linear motion between these keyframes. So with this method, they are able to significantly push the state of the art in frame interpolation for rendered content and are able to obtain production level quality results. So this is generated by their work after doing a 2x interpolation, and yeah, it looks quite, yeah, there are hardly any artifacts, so it's really difficult to make out that there was any interpolation at all. So there are comparisons with some of the other works, and in this work you can see that you could make out certain artifacts here and there, but in their work it's very difficult to do that. So yeah, these are, I'll move on straight. So this is their data set. So generating synthetic optical flow dataset with necessary feature buffers was important for their work. So in order to get texture, they take from static CG images. The flow fields were randomly generated, and some of the outlines were taken from COCO dataset. So it's not really trained in an end-to-end manner. So it's trained in parts, and yeah, and based on that, the networks are fine-tuned to get the final network. So yeah, some more results can be checked out here at their project page. So the limitations of this work is that it can be sensitive to suboptimal auxiliary features, the depth and the normals and albedo, and it cannot really handle complex lighting motion. So next I'll talk about two papers on character simulation. So the first paper is called Trance Flower, a probabilistic autoregressive dance generation with multimodal attention. So in this work, the authors propose a method that generates dancing video of a 3D character which is in sync with the given music. So how this method works is that given motion context, which is joint locations, and given this audio context, which are sound-based features, they extract joint feature representation using this cross-modal transformer, and the transformer output is then fed to this other network, which then outputs the future timestamp joint positions. So to train this network, they collected the dataset of professional and casual dancers using professional motion capture systems. And the dataset that they collected, it has not been released yet, but they say that they will release it soon. And they also collected data of casual and amateur dancers in VR platform. And in test time, they could change the music and produce different dance movement. And, so yeah, you can check out some more results in the project page. So the limitation of this work can be that the baselines that they use for comparison, they are not really designed for this specific task, so they seem rather weak in comparison. And yeah, and checking out some of the other results, I could see that the dance movement seems somewhat repetitive, but yeah, that may be because of the nature of music used, which was rather one-dimensional. So yeah, that might explain why the movement seemed repetitive. So moving on to the next paper. So this next paper by Facebook, it's called Modeling Clothing as a Separate Layer for an Animatable Human Avatar. So this is what the problem setup was. So given an input skeleton, they can generate animatable clothed body avatar with explicit representation of the clothing on the upper body. Their method, it allows for accurate clothing registration, different modeling strategies for body and clothing, and enables clothing texture editing as well. So for data collection, they use motion capture and this multi-view camera setup to capture movement of people like this. So yeah, they collected their own data for this task. So this is the overview of their method. Their method models clothing as a separate layer, and they say that the issue with single layer avatar, in which the clothing is not really modeled as a separate layer, the problem with those kind of methods is that they lack control on clothing states, and the results can be suboptimal as well. And their method, it allows, because they're modeling it as a separate layer, their method allows for better controllability, it allows for texture editing, and the results look bit better. So this is the first part of their method, the clothed body registration and the photometric texture alignment. So in this clothed body registration, they model skin, hair, and pants in the inner layer, and the geometric registration, it does not contain any interior correspondences as they shift across frames. So in the data pre-processing step, they obtain this reconstruction, key points, and segmentation of different body parts, and they use the former two for single layer surface tracking and the latter for mesh segmentation. So I mean, all this is trained in a completely supervised manner, and using surface tracking and mesh segmentation, they get segmented mesh for clothes, which is then registered with a clothing template such as this, and it is deformed onto the cloth garment. And the photometric texture alignment, here they use something similar to a moving average scheme to train the VAE for this purpose. And they do this to learn aligned texture of clothing, which is then applied to the registered clothing surface learned in the previous step here. So the texture is modeled separately from the 3D model. So this is their animation pipeline. They input pose, key points, and viewing directions, and based on the temporal neural network architecture, they generate animated clothed version of the skeleton.
Avatar can create photorealistic animation of a subject. Here, the input driving signal is shown on the left, and the animation output is shown on the right. The animation output can be rendered consistently from different viewpoints with few dependent effects. Notice the dynamic effects of the clothing and wrinkle details produced by our method. The two-layer representation also makes it possible to edit the clothing texture in a temporally consistent manner. In this result, we add the Siggraph logo to the t-shirt. We can also put on some artistic textured pattern all over the clothing precisely without affecting other parts of the body, which is difficult for a single-layer codec avatar without a separate representation of clothing.
So the result that we saw earlier. Here they can add, like they have added Siggraph logo to this t-shirt that we also saw earlier. So limitation of this work can be that it can only model one type of clothing, which is t-shirt in this work. As mentioned, that pants is modeled in the inner layer alongside skin and hair. And their method, it does not really incorporate any physics-based constraints, which might be why they can only model limited clothing dynamics, and it cannot handle body clothing interaction. So moving on to the next paper. So this next paper, it's called Physically Based Neural Simulator for Unsupervised Garment Pose Space Deformation. So here they propose a method to automatically generate pose-based deformed rigged garments given undeformed garments and pose as input. So how this works is as follows. Again, so deformed cloth prediction, it's modeled as a graph neural network, and the losses shown here are the various restrictions and regularizations imposed on the graph vertices and edges. The input skeleton is fed as input to generate deformations, which are then applied to the template cloth, and this deformed cloth is then skinned onto the input skeleton in a proper pose aligned manner to get the final output as shown here. So I'll show some of the results which show that this method works in various scenarios with respect to the body shape, cloth material, pose, and other variation.
Custom avatar with realistic garments with minimal engineering effort. To demonstrate PBNS generalization capabilities, we display numerous and seeing test sequences with no post-processing. As can be seen, predictions show a realistic behavior even under extremely bent joints. Note that all of these models have been trained only on 2500 poses during few minutes.
So these are some of the other results of this work. Yeah, this is result. In this slide we can see an ablation study of this work which validates their overall formation in the form of a physically based neural simulator, in the form of internal energies of the system and everything that they had done. So this brings us to the end of the presentation. Thank you so much for watching.